Right.
Yeah,
But-
31 liters to the ratio.
Yeah, that's it.
Because it's at the same pressure, same temperature.
Exactly. So anyway, most people got this balanced correctly. It was 1 mole of propane, and then how many moles of O2? 5 moles of O2.
3 moles of carbon dioxide.
3 moles of carbon dioxide. What is carbon dioxide?
Yeah.
Yes. And then 4 moles of H2O liquid. So that's right. We also know Avogadro's law. Avogadro says that the volume and the moles are directly proportional. And so if we use Avogadro's law, then we could just use the liter ratio. So like Rolando was saying, this is going to be 1 liter, this is going to be 5 liters, this is going to be 3 liters. Is this going to be 4 liters here? No. Why is that?
It's a different state.
It's a liquid. But I'm only asking for CO2, I'm not asking for water. And so this is a limiting reagent problem. Does everybody see it's a limiting reagent problem because I'm giving you some amount of propane and some amount of oxygen? We don't know. Do we have enough oxygen? Do we have enough propane? Or is this stoichiometric? Stoichiometric means we have just the right amount of both, but we don't know. And so what we do is, for limiting reagent, we calculate the yield. We'll do the yield from propane, from 71 liters of, not 71, 31 liters of propane. And so what we can do is we could skip, since all the gases are at the same temperature and pressure, we can skip the mole part and go straight liter to liter conversion. And so 31 liters of C3H8, and then we'll just use the volume ratio, 3 liters to 1 liter. So this is going to be 3 liters of CO2 for every 1 liter of C3H8. So that's going to give us 93, right? 93 liters of CO2. And so if all the propane reacts, we should get 93 liters of CO2, but we don't know if all the propane reacts because we don't know if we have enough oxygen. And so we have to calculate the yield from 127 liters of oxygen. And so that's going to be 127 liters of O2, and then the volume ratio is going to be 5 to 1. And so 5 liters of CO2 are produced for every 1 liter. Oops, no, it's not. Sorry, it's 5 to 3. 3 liters of CO2 are produced for every 5 liters of O2. And so we'll have to calculate that. So, what is it? 76.2. Now, this often happens. So what do? Do I add these two up to get my total CO2? That is, should I take 93 liters plus 76.2 liters to get my total CO2? Do I add those? Why not? Actually, I don't add these. The reason I don't add these is because once I produce 76.2 liters of CO2, I've consumed all 127 liters of O2. Are there any more liters of O2 to react? No. And so this is what we call the limiting reagent. The limiting reagent is 127 liters of O2. That means there's going to be excess propane left over that's going to be unreacted. And so the maximum amount of CO2 I can generate is only 76.2. I can't get all the way to 93 liters to burn all my propane because there's not enough oxygen. Oxygen is a limiting reagent. I would need to add more oxygen, and then I could burn the remaining propane here. How much propane is going to be left over? I didn't ask that, but we could calculate it. How much propane is going to be reacted depends on the limiting reagent. And so based on this, we have 127 liters of O2 that are going to completely react. Now, how much propane will that react with? Well, we can look at the volume ratio there. 1 liter of propane, C3H8, for every 5 liters of O2. And so this is the amount that's consumed by the O2. So I did the calculation differently in class, but I just want to do it like this. 127 divided by 5. We're going to consume 25.4 liters of propane consumed. And so how much is left over unreacted? Well, that's going to be 31 minus that. That means 5.6 liters of unreacted propane because we ran out of oxygen. So we can't react it. And so it's very common. People tend to add these two, but it's not right. We don't add the two. So 5.6 liters of unreacted. We need more oxygen to react it. And so the yield of CO2 is going to be 76.2 liters. That's our theoretical yield of propane. But the thing is, you have to show this. You have to show limiting reagent. That is, if I give you 2 reagents and you don't show me your calculation from propane, I'm going to assume you didn't know it was a limiting reagent problem. So you got to show the yield from each. Okay, are there any questions on this? The other option is we could go from liters to moles, and then moles to moles, and then moles to liters. We could do that. We would have to do that for water, you know. But for the others, we could bypass it using Avogadro's law. Okay, so I just wanted to talk about it. So again, whenever we have a limiting reagent problem, you have to show the yield from each reagent and then choose the smaller amount. So we aren't going to get this. It's impossible to get 93 liters of CO2. All right, well, we're going to shift gears and go back to what we were talking about last time. And what we're talking about is warming and cooling objects. And so we were looking at the specific heats of different objects. And so we saw the biggest specific heat is liquid water, 4.18, and the smallest specific heat is gold, solid gold with 0.13, or lead. Lead has very low specific heat too. And so what does that mean? Something with a large specific heat means versus something with a low or a small specific heat. A large specific heat means it takes a lot of energy to warm up. So water takes a lot of energy to warm up. A small specific heat means it doesn't take much energy to warm up. So gold warms up rapidly, whereas water warms up very slowly. We're just heating it at the same rate. Then we have other things like granite, glass, concrete, other liquids. All right, so basically that's going to mean that it's not necessarily going to melt, or it's not necessarily going to boil. It could just warm up. So how much energy is required to change the temperature of 25.0 grams of water from 10 degrees C to 50 degrees C? So in this case, are we melting ice? Are we freezing water? Are we boiling, or are we condensing? No. All we're doing is we're adding energy, and the energy is going into warming up the water. Yeah. And so in this case, we have two equations. Whenever we're melting, freezing, boiling, or condensing, that's called a phase change. And so all the energy is going into the phase change. And so let's look at the phase change. Like, what is the boiling point of water?
100 degrees Celsius.
100 degrees Celsius. Does it change?
No. Oh, wait, it does.
Well, it changes depending on where we are, but what is the normal boiling point of water? 100 degrees Celsius. Does normal boiling point of water change? No, because the atmospheric pressure is fixed. And so the boiling point of water is 100 degrees C normally, and it doesn't change. And so all the energy, when we boil water, goes into vaporizing it. It doesn't go into changing the temperature. When we melt ice, what's the melting point of ice? 0 degrees C. So when we melt ice, all the heat we're adding, does it change the temperature? No, all the heat we're adding just melts the ice. That's it. So that's different than in this case. When we add heat to water, we're not at 0, we're not at 100, we're at 10 degrees C. So when we add heat to that, it's not going to melt, it's not going to freeze, it's not going to boil, it's not going to condense. All that heat's going to go into increasing the temperature. And so when we're at a phase change, the temperature is going to be constant. Temperature does not change. All energy is associated with the change in phase. So all heat, which is Q, goes into the phase change. You know, it goes into is, or it can come out, for the phase change. Sometimes we have to add heat to melt ice. In order to freeze water, we have to remove heat, and that's what a freezer does. It removes the heat, so it can cool down. Not cool down, it's already 0 at 0 degrees C if we want it to freeze. And so we have this. Q is equal to the amount times delta H of the phase change. But or just the mass times delta H of the phase change. But when we're not at the boiling point or the melting point, then what happens is we're going to warm and cool. Warming and cooling. Here the equation is going to be different. Q is equal to the amount times the specific heat times delta T. If we're using the specific heat, then the amount is in grams. So it's MC delta T. This is the equation that we use. Is equal to MC delta T. Delta T is T final minus T initial. So this is what we're going to do for this. How much energy is required to change the temperature of 25? So that's Q, the energy or the heat, is the amount of water is 25.0 grams. The specific heat of water is on the previous, it's given 4.18 joules for every gram degrees C. And the temperature change is T final, which is going to be 50.0 degrees C minus T initial, which is 10.0 degrees C. So when we look at the units, the grams cancel, the degrees C cancels, and that leaves us with joules. So it's just going to be 50 minus 10 is 40. Let's go ahead and calculate it. Plus 40. So 25 times 4.18 times 40 is 4,180 joules, or 4.18 kilojoules. Oddly enough, it's numerically the same as the specific heat table. It's just by coincidence. this is just an example of heating, cooling. Now, what happens is this. When we have a phase change, the temperature doesn't change. The temperature is constant. So here's the temperature. And so this would be the melting point of ice. Say. The temperature doesn't change. And then this is the heat. We're adding heat. The heat just goes to the melting ice. But that ice has to start at 0 degrees C. And once all that ice is melted, we end at 0 degrees C. We just end up with water. So we start off with ice at 0 degrees C, and we melt it, and we end up with water at 0 degrees C. The same thing happens here. This is boiling. So we're at 100 degrees C here. So we end up with water at 100 degrees C, and then we add energy, and it boils, vaporizes, until we get to steam at 100 degrees C. The temperature doesn't change. The temperature doesn't change during phase change. And so this is called a heating curve. The heating curve goes like this. But let's say we start off at ice below 0 degrees C. If we have ice that's, let's say, at minus 20 degrees C, then it's not going to melt right away. What's going to happen is the ice has to warm up to 0 degrees C, and then it can start melting. And so this is ice warming up here. Then we have ice at 0 degrees C. And then as we add more energy, it doesn't warm up anymore. It starts to melt until we get water at 0 degrees C. And then when we have water at 0 degrees C, it doesn't boil. It doesn't boil until it gets 100. So we have to warm up the water to 100 degrees C. Then once we have water at 100 degrees C, you can't get it any hotter unless you're in a pressure cooker, because it's going to start to boil. Boil, boil, boil until we get steam. And then once we have steam, then if we keep adding energy, it's going to get superheated. So we're going to have very hot steam. So warming is going left to right, and then we can cool it too. We can start off at steam above 100 degrees C, and then we can cool it down. Steam at 100, and then we can't cool steam below 100 because it's going to condense into water under normal conditions. Once all the steam's condensed, then we can cool the water down, then we can freeze the water, then we can cool the ice down. So this is called a warming and cooling curve. Each section of the curve requires a different equation. And so if we warm or cool, we use this equation, Q is equal to mc delta T. If we melt or freeze, then we use this equation, Q is equal to m times delta H of fusion for melting, or delta H of freezing for freezing. Delta H of fusion and freezing have the same number, because one's negative, the other is positive. We have to keep track of the sign. Okay, then we warm the water, which is what we just did, Q is equal to mc delta T. Then we boil the water. So Q is equal to the amount times delta H vaporization for boiling, or Q is equal to m times delta H condensation if we're going backward. And so for heating and cooling, it doesn't matter. We use the same equation. For phase changes, we have to make sure we use the correct delta H. Then this is warming up the steam. So we could do a more complicated problem. A more complicated problem we take in sections. So let's do this problem. Calculate the total heat transferred when 19.6 grams of ice initially at minus 12 degrees C is heated to steam at 115 degrees C. So what I'll do is I'm going to generate just a heating curve since we're heating it, and then see where we're starting with. Okay, the heating curve, I'm probably not going to completely draw it out, but it's going to look similar to what we just saw. And so let's start off with this. We're going to start off with ice. And how much ice are we going to have? 19.6 grams of ice. And ice is H2O solid. Okay, now when I heat this, this is at minus 12 degrees C. Is it going to start melting immediately? No, it won't. It won't start melting. It won't start melting until it hits what temperature? 0 degrees C. So the first step is I have to warm up the ice. In order to warm up the ice, what's the equation for that? Is it MC delta T or M delta H?
MC delta.
It's MC delta T. So Q is equal to MC delta T. We have to warm it up until we get to 19.6 grams of ice at what temperature? At 0 degrees C. Yeah, we got to warm it up to 0 degrees C. And then it'll start to melt, but let's go ahead and calculate it. I'm going to call this step 1. And so we're going to calculate the amount of ice is 19.6 grams. C, we have to look that up in the table. And so what is the specific heat of ice? Go back to table 15.5. When we go back to 15.5, we see that the specific heat of ice is about half that of water, 2.06. So we're going to plug that in over here. So C is 2.06, the units. Joules per gram degree C. Joules per gram degree C. Delta T is T final. What's T final? 0 degrees C is T final. And what's T initial? Minus 12. So it's T final minus T initial, which is going to give us positive 12 degrees C. So in the first step, to warm up that ice, how much energy do we have to add to warm up that ice? So let's go ahead and do the calculation here. It's going to be 19.6 times 2.06 times 12. And so this one's going to take plus 484.5. So I'm going to just carry mine through. Actually, I'm only allowed 2 sig figs because of this. Unless, yeah. But I want to carry 1 decimal place. Let's do that. Okay, can I get the ice hotter than 0 degrees C? Is that possible? Well, not really, because if I add heat to this, what's going to happen to the ice? It's going to start to melt. And so I continue heating this up, but now what's going to happen is I'm going to go from 19.6 grams of, so this is warming the ice. And now we're at melting the ice. It's going to melt. And so what's the equation for melting? Q is equal to M times delta H of fusion, freezing, vaporization, or condensation? Fusion. Delta H of fusion. Okay, when I melt the ice, I'm going to end up with water. And it's going to be 19.6 grams of water, H2O liquid. At what temperature? What's the temperature of ice water? The water part of ice water is at what temperature? The ice is at 0 degrees C. The water is at 0 degrees C too. And so when we melt this, the energy, the heat does not go into warming it up. The heat goes into melting ice, breaking the hydrogen bonding interactions. Or at least, there's still hydrogen bonding interactions in liquid water, so they're not completely broken because of that. And so we're going to call this Q2. So let's go ahead and calculate it for Q2. Q2 is going to equal the amount, it's 19.6 grams, times delta H of fusion. So we have to go to the table, the other table. Let's go back. and look at the delta H of fusion for water. Delta H of fusion for water is 333 units. Yeah, 333 joules per gram. The grams are going to cancel out, and that leaves us with joules. So, how much? Actually, I'm allowed 3 sixtieths in this calculation. 6,526.8. But I'm going to carry one extra decimal place there. Like that. Joules. So it took a lot more energy to melt it, you see, than to warm up. For Q2. Okay, once I've melted all the ice, there's no more ice to melt. And so if I keep adding heat to it, heat to water, what's going to happen to the water? Yeah, we're going to warm it. So now we're going to warm the water. Warming water. So this is, when we warm the water, what equation do we use?
Q equals MC.
Yeah, Q equals MC delta T. MC delta T. This is going to be Q3. Okay, we're going to keep warming it. And how hot can you get the water? To 100. That's the max. And so we're going to end up with 19.6 grams of water at 100 degrees C. We can't go beyond that because what's going to happen? It's going to start to boil. Okay, so the amount is 19.6 grams. And then we need the specific heat of water.
Okay, so 2.0.
We can find it.
4.18.
4.18. Specific heat of water is 4.18 joules per gram per degree C. And then we need our delta T. So what is T final? 100 degrees C minus T initial? 0 degrees C. So this will be 100 degrees C plus 100 degrees C. All these are positive. It makes a difference, the sign. You know? Positive means we're adding energy. Negative means we have to remove that energy, like a freezer. So if we want to melt this 19.6 grams of ice, it's going to cost us 6,500 joules. If we want to freeze this 19.6 grams of water, we have to remove that 6,500 joules using a freezer. So let's calculate 19.6 times 4.18 times 100. So this is going to be 8,192. How many C? 3,192.8 joules. All right, now when I add heat to it, what's going to happen to the water? Yeah, it's going to boil. I'm not going to get water hotter than this under normal conditions. And so we'll just say boiling water. Boiling water, and this is going to be step 4. And what's the equation for boiling water? Q is equal to MC delta T, or Q is equal to M delta H? And delta H. Now, what delta H do I use? Fusion, freezing, vaporization, or condensation? Vaporization. We need delta H vaporization for water. It's going to be Q4. And so I have to flip to the other table, back. Flip back to the other table. tell me what it is. 2.26
kilojoules per gram.
Yeah. So it's 19.6 grams times 2.26 kilojoules per gram. Nope, the units are different. So far, the units have been joules, joules, joules. But now we have kilojoules. The reason is to vaporize something, you have to completely break it apart. It's going to cost a lot more energy. So they use kilojoules instead of joules. So let's see what it is. 19.6 times 2.26 is 44.2, less 366, 44.29 kilojoules, which is equal to 44,290 joules. 290. And so by far, the first step took about 500 joules, the second step 6,500 joules, the third step took about 8,200 joules, but the fourth step is going to take 44,000 joules, quite a bit more. So this is by far the most. And then once we boil all the water, what are we going to be left with? We're going to be left with 19.6 grams of what? Steam, which is H2O gas. At what temperature?
115 degrees.
Well,
Yeah,
at 100 degrees C. That means there's a fifth step here. The fifth step is, once we boil all the water, there's no more water to boil, so as we add energy, what's going to happen? It's just going to get hotter. But how hot can we get it? Well, they don't want it to get too hot. They want it to get to what temperature? 115? That's where they're telling us to stop. They're telling us to stop at 115 degrees C. So we're going to end up with 19.6 grams of steam, H2O gas, at 115 degrees C. So that's given. We could have made it even hotter or cooler. Depends. And so what's the equation for this that we use? Q is equal to MC delta T. Step 5. So the mass is the same, 19.6 grams. C, we need the specific heat of steam. So let's look that up. What's the specific heat of steam?
2.00.
Yeah, it's pretty close to ice. About half that of the liquid. So it's 2.00. Units would be joules per gram degree C, and delta T is T final, 115 minus 100. So delta T is going to be 15 degrees C. Gives us 268. So plus 15 degrees C was the temperature increase, and then just go ahead and calculate 19.6 times 2 times 15. 588. Only allowed 2 sig figs, so 580 sub 8 joules. All right, so those are the steps it's going to take to do this. So what we can do is we can overlay that on the curve here. So here we're starting out ice here at minus 12 degrees C, and then we got to warm it up. So that's the first step here. It's going to take about 444.5 joules to do that. Let me erase this here. Let's leave that there. So we're starting off at minus 12 degrees C, and we have some ice there. And the first step is the ice has got to warm up to what temperature?
0.
0. So we're going to go up to 0 degrees C, at which point we can't get any warmer than that. And so this first step, how much energy is this first step going to take? 484.5. 484.5 joules. Okay, this is step 1. Okay, once we're here, then what's going to happen to the ice at 0 degrees C, and we keep adding heat? It's going to melt. It's going to take a lot more energy, right? To melt. Yeah. In order to melt all of it, it's going to cost us 6,526.8 joules. That's step 2 here. We're going to melt all the ice. Once we've melted all the ice, then it's going to warm up. Once we've melted all the ice, we have water now. And so we need to warm up the water. What's the maximum temperature?
100.
100 degrees C. This is step 3. How much energy is this going to take? 8,192.8 joules. Okay, then once we've warmed up the water to 100 degrees C, so we're at 100 degrees C now, what's going to happen as we add more energy? It's going to boil, vaporize. And how much energy do we have to add to get it to vaporize? Well, 44,296.
296.
Maybe about here. Sorry, I went too far. Just guessing. So let's say to boil that, it's going to take 44,296 joules to boil it. This is step 4. So warming, melting, warming, boiling. Boiling by far is taking the most. And then once we heat all that steam, once we boil all the water, then we're going to heat up the steam in the last step to what temperature? 115. So it'll be 115 degrees C here. And so this is going to be step 5. Step 5 is only going to cost us about 600 joules. So 588 joules. So altogether, how much energy did we use? A lot. And so what we have to do is we have to add these. Unlike that limiting reagent thing, we don't add those, but in this case we have to add it. And so the total energy, this is going to be Q total. Q total is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. However many steps there are. In our case, we have 5 steps. So let's go ahead and add it together. So end up with 60,088 joules, or 60.1 kilojoules. No, I guess we could go one more. 60.09. Sorry, 60.09 kilojoules. Looks like we're okay. Oh no, sorry, this one's only one digit. 60.1 kilojoules. Correct numbers. right, so this is the curve they got. You know, again, warming the ice, melting the ice, warming the water, boiling the water, heating the steam. And they called it A, B, C, D, E. I called it 1, 2, 3, 4, 5. And so they're doing the step-by-step calculations, which we did. So let's see what they end up with. This is the total, they're just going to add them all up. We got 60.1 kilojoules. So. Okay, any questions on this? Let's take a break now. Start.